The results you will see today are the work of a group of researchers at the University of California, Irvine. Our work is focused on the relationship between impurities in tantalum powder feedstock and the mechanical properties of the resulting cold spray coating. It was motivated by the differences in mechanical behavior of two different coatings produced from nominally identical tantalum feedstock powders, differing only in the concentration of interstitial oxygen and hydrogen impurities introduced during processing. Three-point bend test data revealed that the hydrogen-rich coatings displayed lower strength and far more brittle behavior. While there was a difference in particle size distribution, the initial hypothesis was that the hydrogen content played a dominant role in the bonding and deformation mechanisms during cold spray processing, and it was consequently the focus of this study. Molecular dynamics simulations revealed that hydrogen interstitials initially decrease strength and stiffness in the perfect lattice. Later on, interaction of hydrogen atoms with form defects increases lattice strength. Ductility remains unaffected. Different techniques were used to characterize the microstructure of the coatings. Average porosity was calculated through image analysis of backscattered SEM images, and a small difference was found. Backscattered SEM imaging was used to identify and map microstructural features within the two coatings, while PEE data was used to characterize the boundaries along particle-particle interfaces as a function of misorientation. However, no clear differences were observed between the two coatings. PEM and EDS revealed segregation of oxygen to unbonded boundaries within the coatings. However, no clear difference between the two coatings was identified. Micropillars with an aspect ratio of 2:1 were carved and loaded in uniaxial compression. Shear bands and localized failure are consistently observed near the splat boundary regions. Both feedstocks exhibit statistically equivalent strength and ductility at the microscale. In conclusion, besides the small difference in porosity percentage, no definitive differences in microstructural features or evidence of hydrogen embrittlement were observed with the techniques adopted so far. The lack of obvious microstructural and micromechanical differences between the two coatings suggests that the splat boundary network is primarily responsible for the micromechanical differences. Moving forward, the first step is to repeat the tests and analysis presented today, but under tension conditions. We also want to further explore the behavior of the native oxide layer during cold spray deposition through molecular dynamics simulations. And lastly, in order to deconvolute the effects of multiple variables, two different studies have been put into motion. The first one will systematically vary the interstitial hydrogen content in the powders, while the second one will systematically vary the particle size distribution of the powders. The authors would like to acknowledge the following.